Welcome back class to our course on mechanical behavior of materials part 2. So in the last lecture we discussed about the variation of plastic zone size with respect to theta. Okay, so overall we were able to figure out what is the plastic zone shape for Tresca and von Mises criteria in both plane stress and plane strain condition. Okay. So now we'll discuss about the variation of stress intensity factor with different geometries, and then we will also discuss about fracture toughness. Okay, so let's proceed. So during the derivation of inlet stress or stress ahead of the crack tip, you remember the sigma 11 was given as sigma infinity root pi a divided by root 2 pi r, then cos theta by 2, 1 plus sin theta by 2, sin 3 theta by 2. Okay. And then we had written this as f theta also. Now this particular term, you remember we had denoted this as K1. Okay. So K1 was sigma infinity root pi a, where sigma infinity was far field stress. Okay. So now we'll just use sigma as sigma infinity. So K1 is sigma root pi. Okay. And if you remember, this was for infinite plate. The whole derivation was made for infinite plate. Okay. So your thread dimension is much smaller than the dimension of the plate. Okay, we had discussed this. So now what happens when the plate width is finite? Okay, what happens to the value of T1? So let's talk about that now. So let me draw a schematic of line of forces. We had discussed that before. So if we have infinite plate, okay, and then there is a track here. And it is under applied stress of say sigma. Okay. So now if we draw a line of forces, you remember it will look something like this. So we have all these are line of forces, imaginary lines. We had discussed this when we were talking about stress concentration. So equally spaced line of forces. Then it will go down like this. So I can do for all other lines. Okay. So if you remember, there is a bending of line of forces at the crack tip, and that is what it led to stress concentration. something like this. Okay, so let me just draw fast, and then the deviation is going to be less, okay, at the end. Okay, and we have stress concentration here in these two regions. Okay, so this is for infinite plate. Now let's consider there is a finite plate under the same applied stress. Okay, so now I am drawing a finite plate. If you see the boundary is not zigzag. Okay? So I'm drawing a finite plate which has this track. Something like this. Okay. So this is your finite plate. So it has some width and infinite plate. It also has width, but the dimension of the plate is much higher than the track length. Okay. So now if the finite plate is under the same applied stress, all these stress lines, so suppose we have these stress lines or stress trajectories or line of forces, say n numbers. Okay. Since the applied stress remains same, this n number of line of forces, this needs to be fit inside the finite plate. Okay. So in the infinite plate, since the plate is infinite, these line of forces had chance to bend and maintain some distance, right, between line of forces. But in finite plate, all these line of forces, see, line of forces will remain same. So suppose the line of forces in infinite plate is n. So same will be there for finite plate because applied sigma remains same. So now all these line of forces need to be squeezed in the given width of say 2W. Okay. So if you just visualize that this n number of line of forces are getting squeezed in this 2W, the stress concentration ahead of the thread tape here in the finite plate is going to be higher than the infinite plate, isn't it? Because all the line of forces are now getting squeezed between this width here, right? And previously, this line of forces had chance to, spread throughout this whole width because the plate was infinite. So if you have finite plate, there is more stress concentration at the thread tip than the infinite plate, considering the applied stress remain same. Okay. So suppose the line of forces, total line of forces is n. Okay, again, remember these line of forces are imaginary lines, and we use this to make you guys understand how the concept of stress concentration. Okay. So line of forces are near or close to each other at the thread tip, but distance between them increases as one moves away from the gravity. Okay, so that is point number one, and that leads to the stress concentration. Now the red line, so the red one is your infinite plate. Where bending of line of forces is possible because the width is too large. Okay. So bending was possible because width is too large. Now in the case of the purple one, which is the case of finite plate, all n number of lines have to be inside the plate. Okay. This means all line of forces needs to get squeezed okay, so they will have to be squeezed in the given width of 2w. Okay. So this also means that line of forces there may multiple lines, okay, have to be closer to get accommodated. In the width, in this case 2w. Okay, so the line of forces first they need to get squeezed between in the plate of width 2w. That means the line of forces will be much closer as compared to the infinite plate. Okay, and if this happens, this will lead to increase in the stress and the gravity. Okay, that means stress will be higher, or say stress concentration will be higher in the finite plate than infinite plate. Okay, so here we are maintaining sigma same and track length remains same. Okay, so now let's compare what happens to stress intensity factor. So if you remember, K1 is sigma root pi a. This is for infinite plate. Okay. Now sigma is same. So this is same. A is same when we are talking about a finite plate instead of infinite plate. So sigma is same, A is same, but K is higher, right? Because of the squeezeness of the line of forces we just discussed. This means we can write K1 as Y sigma root pi A. So we are introducing a term of Y, which is a factor which is called structure factor, and the value is going to be greater than 1 because K1 is going to be higher in finite plate, right? So for finite plate, we can write stress intensity factor as Y sigma root pi A, where Y is called structure factor. Okay, and its value will be greater than equal to 1. So Y is equal to 1 when plate is infinite. Okay, so if Y equal to 1, K equal to sigma root pi A. So this is for infinite plate, and Y greater than 1 when plate is finite. Okay, and Y here will depend upon the geometry. And loading condition. Okay, so again remember Y is equal to 1 for infinite plate, and as soon as we talk about finite plate, you have to introduce a factor of Y. And for different geometries and loading condition, Y is going to vary. That means K1 is going to vary. Stress intensity factor is going to vary. And now we are going to discuss about that only, that what is the expression for K for different geometries of plate. Okay. So now several points can be made up. A few points can be made from the above discussion or whatever we discussion or by above discussion. The first point is finite width will have more stress concentration or higher stress concentration than infinite. Okay, so here we are saying sigma is same and length of the crack or crack length is same. So if we have two plates, one is finite plate and another one is infinite plate. Now if both the plates are under the same applied stress and the crack length at the center remains same, finite width is going plate will have higher stress concentration at the crack tip than infinite plate. Okay, and we discussed this using the line of forces. That is point number A. Point B is width, decrease in width of the plate. They will be increasing increase in the stress concentration okay, and this will lead to increase in T. Again, we are having sigma as same and crack length as same. So now let's consider two plate. One is small W1 and W2. So we have two finite plates. Crack length remains same in both the cases. So this is a W1 and another plate. This is also finite but having higher width. This is W2. So W2 is greater than W1. The crack length remains same here. So this is 2A. This is 2A. And both are under the same applied stress of sigma. Okay. Now, if you just draw the line of forces or stress trajectory, you will eventually see, right, that if the width is smaller, or in this case W1, the stress concentration in W1 is going to be higher because all the line of forces, they need to get squeezed in W1, which is smaller width. Okay, so the line of forces will be much closer in W1 as compared to W2. That means the stress concentration will be higher in W1. This also means that the stress intensity factor is going to be higher in W1. Okay. That is point B. Point C, for the same width, say W, increasing the crack length will increase stress intensity factor. Okay. So again, if I draw a schematic, so same width of the plate in both the cases. Okay. So say this is W, this is W. So this is plate 1 and plate 2. They are under the same applied stress of sigma. So in one case, we have crack length as 2A1, and in another case, we have crack length of 2A2. So we can see here 2A2 is greater than 2A1. Okay. Now, if you again use the concept of stress trajectories or line of forces, you will see that in the plate 2, the line of forces will be much closer than in the case of plate 1. Okay, remember the number of line of forces in both the cases will remain almost same. Okay, so in plate 2, you are going to observe higher stress intensity factor as compared to plate 1. So these are the 3 points we can have when we consider finite plate and infinite plate. So overall, if you see in the finite plate, K will depend upon both track length and width of the plate. Okay, so K will be function of A by W. You will see it eventually. So in both the cases, in the finite plate, the stress intensity factor depends upon the crack length and width of the plate. In the case of infinite plate, if you remember, the stress intensity factor was varying with only with respect to A. There was no concept of W there because A is much smaller than W. Okay. So if I plot, so for infinite plate, for all practical purpose, A by W tends to 0 as W is much higher than A, right? And if you remember, this was the definition of infinite plate. Okay, so for infinite plate, A by W tends to 0. So now if I take a plate of say width 2W, it has a track of length 2A, okay, and it is under applied stress of sigma. Okay, so if I plot Y, which is structure factor, which is a function of K1 by sigma root pi A. Okay, so I'm plotting Y versus A by W. And we know that as A by W tends to 0, the plate becomes infinite. And in an infinite plate, the structure factor is 1. Okay, so it will start from 1. And then it is going to increase as A by W increases. Okay? So this corresponds to infinite plate, where A by W tends to 0. And then for different A by W, you can plot what is A and you will see it is going to increase. Something like this. So it varies. Okay, so it increases as A by W increases. Okay, goes like this. So why the structure factor increases as A by W increases. Okay, so now if I plot this nicely in say MATLAB or even in Excel, you can obtain this line, fitting curve. So there will be some expression for Y with respect to A by W, which is this fitting curve here. Right? So that expression will be given as Y equal to sec pi A by 2W square root 1 minus 0.025 A by W square plus 0.06 A by W 4. Okay. Again, remember this is for a finite plate because we are getting expression of y, and the crack length is 2a. The crack is at the center and the width is 2w. Okay, and you are under an applied stress of sigma. And if you calculate y, the expression for y for that particular configuration of plate will be given as this, which is this fitting curve. Okay, so that expression belongs to this fitting curve. So we know the expression for y. Now we also know what is k. K is y sigma root pi a. That is a general expression for stress intensity factor. Now for the above configuration, so for this particular configuration here, what is sigma? So if now let's talk about load, because typically we have the load and then we can calculate sigma if we know the area, right? And remember, sigma here is far field stress, right? So if it is under an applied load of P, we know what is 2W, right? And if we know what is thickness in terms of B, so we can figure out what is the applied stress or far field stress sigma. Okay. So this particular configuration, sigma can be given as, so for the configuration, sigma will be load by area. So P divided by 2W into B. Okay. Where 2W is the width of the plate and B is the thickness of the plate. Okay. That means area is 2W into B. So far field stress will be given by P by 2BW. Okay. So let's put this sigma in the equation of K, general equation of K. So this K here, this can be written as K equal to Y sigma root pi A. So sigma is P by 2WB. And now let's put the value of Y, which is sec of, so here we will also have pi A. Okay, because it's y sigma pi a, sigma is p by 2 wb and then pi a. So this becomes, now we are putting the value of y. Okay, so this will be given as this. Okay, or we can write this as p by b root w root over pi a by 4w sec pi a by 2w and then this whole expression. Okay, so 2 I just moved inside and then pi a also I moved inside. So this becomes p by b root over w. Okay, so this particular term here, we can write this as f a by w. Okay, so overall k can be written as p by b root w f a by w. Okay, so in general k is y sigma root pi a. Okay, and in terms of W, we can write K as P by B root W F A by W. So if we can figure out somehow FA by W for different geometries of plates, we should be able to figure out what is K, isn't it? And we also know P, B, and W because we know the plate. So everything is known. We should be able to figure out what is K. So we know the stress distribution in front of the thread tip. So now basically what we have to do for different geometries, we should be having the expression for FA by W. Okay? And that is what I'm going to write now for different configuration. So now you will also see what different geometries we use in fracture mechanics. So I'm just going to give you 2 or 3 important ones. Okay? So K1 solutions for common test specimen. So the values, whatever the expression I am writing is for FA by W. So if you know FA by W, you can calculate what is K. So the first is your common one, what we have discussed till now, which is central track. So you have a plate of width 2W. The load is P and the track length at the center is 2A. So for this particular configuration, which is known as CCT, center track tension. So the track is at the center and we are having tensile loading. So the name is CCT, which is center track tension. Okay. And for this, FA by W is given as root over 4A by, pi A divided by 4W sec of pi A by 2W, and then our expression with respect to A by W, 2.025. So this we just saw before. A by W square plus 0.06 A by W 4. So this is configuration A. Let me change it to capital A. Otherwise, there will be confusion between small a, which is the track length also. Okay. Now, second configuration is called single edge notch tension, which is SENT. Okay. So it will be something like this. So load is P. Now here W will be given in terms of only W, not 2W, and track length is A, not 2A. Okay. So this is SENT, which is single edge notched tension. Okay, single edge notch tension. At one edge, we are going to have notch, a crack, right? So the name is single edge notch, and tension is being added because the load is tensile. So for this, the expression is root over 2 of 10 pi A by 2W divided by cos of pi A by 2W, and then expression in terms of A by W. So 0.752 plus 2.02 A by W 0.37, then sine term here. Okay. And the last one is one of the most important one is called compact tension, and we use it, during fatigue testing a lot. We are going to discuss about fatigue test, and there you will see whenever you want to discuss about the application of fracture mechanics in fatigue crack propagation, we all often use compact tension specimen. Okay. So the configuration is something like this. So this is pin loading. So the previous two, if you see, we have drip. Okay. Here it is pin loaded sample. So the drawing is not very nice, but conceptually you should understand. Okay? This is 1.25 W, and the W will be measured from the center of the pin. So this is center. So this is W. Okay, not from the edge. It will be measured from the center of the pin. Similarly, A will also be measured from the center of the pin, not from the edge. Okay, so A is known, W is known, and the height is going to be 1.25 times W, and then there is going to be B, okay, which is thickness. So it's like this. So in all the cases, you have thickness B. Okay. So for this, which is called CT, compact tension, F A by W will be given as 2 plus A by W divided by 1 minus 8 by W 3 by 2, and then expression with respect to A by W, which is 0.886 plus 4.64 A by W 13.32 A by W square plus 14.72 A by W cube minus 5.60 A by W 4. Okay, so these are three most important configurations. We have SC and B also, okay, single edge notch in bending. Then we can also have double edge notch tension. So there are different configurations. Okay, you can have penny shaped crack also. So for different configuration, there are lots of books where you will find the solutions for A by W. And if you know A by W, you can figure out what is K, right? Here, this equation. Okay, so you have to first calculate F A by W and you should be able to figure out what is K. Okay, so if you go through books, you will be getting more number of solutions for different configurations. So this is what I have got. In some of the books, you will see some deviations from the whatever expressions I have given. Okay, but overall the essence remains same. So overall, if you see, A1 is P by B root W F A by W. Okay, where B is your specimen thickness. Okay, and if I just roughly plot, so not up to the scale, but it will give you some idea how F A by W varies. So F A by W with respect to A by W. Okay. So for infinite plate, so remember the infinite plate is this value here because A by W tends to 0 there. Okay. So the value is going to be, so if I just mark here 5, 20, 10, 20, 25, like that. So, and this is 0. A by W is say 0 0.2, 0 0.4, 0 0.6, 0 0.8, and then 1. Okay. So again, I am drawing a rough sketch. It is not up to the scale. So if I just place A by W tend to 0 for compact tension, it is going to be nearly 2. Okay. So if you see this equation here, so if I place A by tends to 0, so all the term here, all these terms will be 0. Right? So it will be 2 times 0.886. Okay. So it will be roughly 2. Okay. So it will be somewhere here, the value of compact tension. And then it is going to increase. Something like this. For SENT and CCT, if A by W tends to 0, the value goes to 1. Okay, because set, if I talk about now CCT, set A by W is 1. All the right term here, in term the expression here, it will be 1, but A by W is here, right? So this is 0. Similarly, for SENT, it is going to be 0. So it will start at 0. Let me change the color. It will be something like this. And then 1.8, something like this. This is for, so this is for compact tension. This is for SENT. And the last one is for CCT. Again, rough sketch, huh? Not up to the scale, but just for understanding, I have drawn here. Okay, so now we know the expression for compact tension, SENT and CCT. Okay, so now let's talk about SENT a bit. So for single edge notch, tension which is SENT. Okay, so now if I talk, say SENT, you should know it is single edge notch tension. Why? We know it can be given as FA by W root W by pi. Okay, that is equation number 1. We have discussed this before. Okay, we also know K can be given as P by B root W FA by W. Okay, this is equation say 2. So we, sorry, this one we don't know. We have to prove this. So for single edge notch, we have to prove Y can be given as FA by W root W by pi A. Okay. And why we are doing this? So if you remember, K can be given as Y sigma root pi A. Okay. Sigma is known. If we know Y and A is also known, we can calculate sigma. Okay, so we have to just, and we know the expression for FA by W. So if we can calculate FA by W, we can calculate what is Y. So we can calculate K. Okay, so this is now equation 1. And we also know A1 is Y sigma root pi. So equation 2. So now we will combine equation 1 and 2 to prove the above expression. So from 1 and 2, we can write Y equal to P by B root W F A by W divided by sigma root pi A. Okay, just combine equation 1 and 2 and you will get this particular expression for Y. Or we can write Y equal to F A by W and then P by B root W, then root pi A. Then we are writing BW by P, okay, where sigma is P by BW. You remember SENT for something like this? So this thickness here was B and the width was W. Okay. So the cross section area is BW and the load, whatever we have here, is P. So sigma is P by BW. So we are just putting that value here. Okay. So Y now can be written as F of A by W root over W by I. So we have proved the above equation. Okay. So now we know the expression for Y in terms of F A by W. And we also know what is F A by W, the table, all these values. Huh? So this is for F A by W. Okay. So now let's see what happens when the single edge notch tension is infinite. Okay. Or semi-infinite because one side is fixed. So we know Y equal to F A by W root over W by pi. Okay. And general equation for SENT is for F A by W is over to 10 pi A by 2W divided by cross of pi A by 2W and then expression for A by W. So 0.752, 2.02, 1 minus sine of pi A by 2W whole cube. Okay. So this is for SENT. Now, if let's say we place a limit of A by W tending to 0, so it is like semi-infinite. So if I draw for the specimen for that, it will be something like, so one side is fixed, right? And then zigzag. So this is like semi-infinite plate. Semi-infinite plate. SENT. Okay. And by definition, A by W is tending to 0 for semi-infinite or infinite plate. So we will take a limit of A by W tending to 0. Okay. So if we do that, so limit of A by W tending to 0, we need to calculate what is F A by W so that we can calculate what is Y from this particular expression. So we can write this as 2 10 pi A by 2W pi A by 2W into pi A by 2W. So we are just multiplying and dividing it by expression of pi A by 2W. The bottom one remains same. Okay. And then the right hand expression remains same. So I'm just, okay. So this is same as this. Okay. We can further write this as, so it's like 10 theta by theta 10, where theta tends to 0, limit that becomes 1. So the expression now will be root over 2 pi A by 2W, and the cos pi A by 2W as 8 by W tends to 0, that this expression becomes 1. Okay. And similarly, I just mentioned that this particular expression also becomes 1. Okay. So now you have 0.752 plus all these value. Okay. Let me write down 2.02 A by W plus 0.371 minus sine of pi A by 2W whole cube. Okay. So as A by tends to 0, A by W, this becomes 0, this becomes 0. Okay. So overall, you are going to have 2 pi A by 2W and then here 0.752 plus 0.37. Okay. Or limit A by W tending to 0, f of A by W, this becomes 1.12 root over pi A by W. So we have got an expression for f A by W for semi-infinite plate, SENT. Okay, remember if the width is fixed, then we have to use FA by W, whatever is shown here, okay, on the top. But since we are talking about semi-infinite plate, we have an approximation of A by W tending to 0. So the expression for FA by W becomes very simple, which is 1.12 root over pi A by W. Okay. So if I write this as say equation number 4, okay. So now use 4 and place f A by W there to calculate what is value of y for semi-infinite plate. So place value of f A by W in equation 4. So that will give you y as 1.12. Okay. And again, remember, this is when A is much smaller than W. That means A by W is tending to 0. So for semi-infinite plate or semi-infinite SENT plate, Y is always 1.12. Okay. And if it is not semi-infinite, if it is finite plate SENT, then you have to calculate, you have to place all the value of A by W and calculate what is F A by W to figure out what is going to be the value of structure factor Y. Okay. So remember again, Y equal to 1.12 for semi-infinite plate, and for finite infinite plate, Y is always equal to 1. Okay. So let's see Y equal to 1. Let's prove that also very quickly for CCT. So we know for CCT, Y equal to 1 for infinite, say infinite plates. Let's prove that also very quickly. So F A by W we can write as okay. So this is for CCT. So your applied is T. Then say thickness is B. And then you have rack length of 2A and width is 2W. So this is CCT. So FA by W is given by this, and we also know K1 is P by B root W, F of A by W. Okay. So this is say now equation 1. So I'm writing again equation 1 for CCT. We also know K1 is Y sigma root pi A. Okay. Or Y sigma here is going to be P by cross section area, which is 2W into 2A, and then root pi. So this is equation number 2 for CCT. So from 1 and 2, we can write P. So I'm just equating K1 in 1 and 2. Okay. So P B root W F of A by W. This will be equal to Y P by, okay. So here I made a mistake. It is not 2A, it is P by 2W into B. Okay. So this is 2WB root pi A. And we can write Y as F A by W 2 W by pi. So this is the expression for CCT. We had already calculated the expression for SENT. Okay. So now if I place limit of F A by W tends to 0, which is the case for infinite plate, okay, we can write so I want to now say, so let me put this equation as 3. Okay. So from equation 3, F of A by W. So here limit A by W tending to 0. Okay. So sec of pi A by 2W, that is going to be 1, and A by W square, A by W4, that is going to be 0. So this will turn out to be pi A by 4W. Okay. So let's see now, this is equation 4, and now we have got equation number 5. So if we combine equation 4 and 5 from 4 and 5, y equal to F A by W, that is pi A by 4W, and then 2 of root over W by pi A. So y is coming out to be 1. So we already knew that. Okay, so I just proved it again for infinite plate. Okay, so overall we have discussed about stress intensity factor expression for different configuration or geometries of plate. For CCT infinite plate, y equal to 1, and for SENT, since one side is fixed, it is semi-infinite SENT plate, y is going to be 1.12. Okay. So I will stop here and we will meet again in the next class. Thank you.